Right, so good afternoon. This is EE2020. Sorry. As in the previous years, that this is a small class compared with the next door. Okay, and as you can see from the syllabus that we'll have a quiz every week. And I believe that you have joined the first quiz last night. So if you missed the first quiz, that's okay, because in total we will have 15 quizzes in this semester, and I will count the highest 10 scores in your quiz examinations. All right, so you can mix at most 5 quizzes. Okay, so there is no makeup quizzes if you have anything to be absent from the quizzes. Yeah, but if you need, you have to be careful that don't miss the quiz examinations more than 5 times. All right, so I think I will begin with the lecture. Yes, please.
Can we change the time for the presentation class? Because I have another presentation class that is at the exact same time.
Exact same time. Yeah, that.
Both of them have quizzes in the class.
I see.
And since this class is smaller, I hope I can.
Well, the reason why I pick up the Monday evening is because that it's a good time to have the quiz, because it's a kind of a review of the materials taught in the previous week. And also you will have enough time to prepare the quiz, because you have a weekend at least. I think so. So if you have a time conflict, there is one resolution that you can take the quiz exam earlier. Yeah, for example, you can take the quiz at 5 p.m. on Monday. If you have no other class, 7, so you have class in the. Yeah, you can. Take it with the TA to arrange another time. Yeah. So, but you will miss the recitation. Yeah, right. Yeah. So you can be arranged that if you can take the quiz examination on Monday, the same day, before or after the normal time. Okay, but if it's a late night, I think it would be not convenient for our TA. So you have to discuss with our TA. All right? Okay. Other questions? Okay. And I will distribute my lecture notes to you. Okay, so you're not necessary to take notes, but of course, if you can take the notes as you wish, but I think it's not necessary. And then in the meantime, we will record the class lecture. So if you want to review my class lecture, you can go online. The TA will put the recorded lectures in my YouTube channel. Okay? Yeah, YouTube channel. I have a channel. So you can, if you are interested, you can watch my linear algebra lecture course or probability courses before, even some class in graduate school. Okay. And anyway, because we are a small class, so if you have question, you can interrupt me anytime. Okay, by raising your hand or just call me, all right? So don't be hesitate to ask me any questions. Okay. Okay, so basically we have 3 parts in this semester. The first part is about Fourier analysis. The second part is about partial differential equations. And the third part is about complex variables. My planning is that for Fourier analysis, I would like to give you a very comprehensive overview of this subject. Okay, so since I will distribute my lecture notes to you, many the proof, many theorems will be mentioned in the class lecture, but you will have the detail of the proof in my lecture notes. Okay, so you can study by yourself. And of course, if you have any question about my lecture notes, you can ask the TA in the recitation class, or you can send an email to me, so we can discuss sometimes in person, or sometimes we can arrange the online, for example, by using the Google Meets. Right? So there are quite a few ways to discuss with you. Okay. Yes. Oh, well, I'm sorry, because I haven't yet to send the first notes, because I found out that I need to correct some errors. So, okay, but I think I can send you the notes today, maybe at night time, until I correct some of the parts of my lecture notes. Okay, right? Okay, so, okay, and basically I will follow the guideline of the textbook, and of course the material will be more comprehensive than the textbook, but I heavily rely on the examples as well as the exercise given in the textbook. Okay, so as you can see, when you assign the first homework for the first grades, you can see that all the problems taken from the textbook by Quasic. Okay, so, and I believe you have the same textbook used the last semester when you learned the ordinary differential equation. Okay. Right, so chapter 11 is about Fourier analysis. All right, and the first section is about Fourier series. Okay, first of all, I would like to define the concept of periodic function. I believe some of you know this concept before. Okay, so a complex or real-valued function f, okay, defined on the real line. So real line is denoted by R. So R is the set of all real numbers. Okay. It's called a periodic function. All right. So if there exists a constant p greater than 0, so it's a positive constant called a period of f such that f of x plus p is equal to f of x for all x in R. Alright, so for example, if for f of x is equal to 1 for all x in R, so this function is a constant function, okay? And for a constant function, it is a periodic function because you can select any positive p, right? You can select any positive p, so that so for any positive p, we know that okay. So any positive p can be a period of a constant function. Okay, so constant function is a very special periodic function. Okay, and the second function, say the sine x. Okay, so this is the sinusoidal function, and now so we know since f of x plus 2n pi, okay, is equal to sine x plus 2n pi. And also our understanding about this sinusoidal function in high school, we know that this is sine of x here, okay, and so we have that, okay, for all n in z. So what is z? Z is the set of all integers, including negative integers, 0, and positive integers. Okay, so alright, so we see that 2n pi is a period of this function for any n greater than equal to 1. I'm sorry. Okay, because we asked that p to be positive. I'm sorry. So should be not all integers. I have to say the set of all positive integers, the capital N here. Alright, so you see that a periodic function can have infinite many period in general, okay? But the smallest period of a periodic function okay, f is called the I forgot to put a non-constant. Sorry about that. The non-constant periodic function is called the fundamental period of f. Okay. Right, because for any constant function, there is no fundamental period. Why? As we have seen, any positive p can be a period of a constant function, and this p can be as small as possible. Okay, so that we can't find the smallest one. But for non-constant periodic functions, there is one and only one smallest period, and so that is called the fundamental period of function f. Alright, so you can see f of x sine x has a fundamental period 2 pi. Okay? So sine function has a fundamental period 2 pi. Okay, so we can observe that 1, the constant function 1, as we mentioned before, sine x 1 cosine x sine x cosine 2x sine 2x etc. cosine nx sine nx, right? So we have an infinite sequence of sinusoidal functions, alright, in addition to these constant functions. So these functions are, we know they are periodic function. Okay, and this function, okay, with a period, so they have a common period called 2 pi. Okay, so they have 2 pi, but even though 2 pi is the fundamental period of cosine x and sine x, but 2 pi is not the fundamental period of cosine 2x. So what is the fundamental period of cosine 2x? It is pi. Okay, it is pi. Right. But the common, the one thing you can say that they have a common period called 2 pi. Okay, so they have a period 2 pi, and which from the so-called trigonometric system so they are called trigonometric systems. Right? So whenever we refer to the trigonometric system, we mean this is sequence of functions. Okay, and the trigonometric system play an important role in Fourier analysis. Okay. Okay. Any questions, Saturn? Alright, now so I list the first theorem in the textbook, which is quite simple. It is called orthogonality of the trigonometric system. All right, and the statement is here. The functions, okay, in the trigonometric system okay, so the functions in the trigonometric system, these functions are orthogonal over a specific interval, this goes interval minus pi to pi. So this interval has length which is equal to 2 pi, And 2 pi is just a period of functions in a trigonometric system. Okay. The meaning of orthogonality is specified in the 3 items. Okay. So the integral of the cosine function over this interval from minus pi to pi is 0. Okay, and it is also equal to the same the integral of sine nx over the same period, over the same interval. First of all, second, that the integral of the product of 2 cosine function, okay, is also 0 if n and m are different, right? And this is the same for the sine function. Okay, so if you multiply 2 cosine function, or you multiply 2 sine functions, okay, but with different n and m, then their integral will be 0. The third one is that the product of cosine function and sine function, okay, and the integral over their product is also equal to 0. Okay, for all n m greater than equal to 1. And so even n equal to m, even n equal to m, cosine nx, sine nx, okay? This product can have a 0 integral over the interval from minus pi to pi. Okay. Okay. So in particular, if you like, you may wonder, okay, in the statement of the theorem, okay, whether the first function, this common function, so does this particular function take any part in the theorem? And the answer is yes. Because why? Because you can tell me this is 1 times, right? So 1 times the cosine function, right? The product is 0. And also 1 times, okay? So they are you mean more than 2? Well, I think because we are talking about that the mature relationship of the functions in the systems. Okay, so if you pick up any 2 function from this list. Either maybe this function or one of the sine function, right? Or the cosine function or one of the cosine function. Then you take the product of both of them, and then do the integration, you get a 0. Okay, so it's about the mutual relationship, right, between the functions in the trigonometric system. Mutual means that mutual means that you and me, okay. MUTUAL, yes. Yeah, mutual. So that's about a mutual relationship. Between functions in the trigonometric system. Okay, so mutual is you and me, between just two objects or two persons. Okay. Okay, so that constant one and one cosine, constant function and one sine function, okay, and cosine and sine, okay, cosine, any sine functions, okay. And how about the same relationship, cosine with cosine? This is the relationship, and this is sine with sine together. Okay, so this is 3 items which illustrate all possible mutual relationship between two functions, two functions in the list. Okay. Okay, so basically you randomly pick up two functions from this list. So this function and that function together, okay? Then this case is here, in the third case here. Okay, and the integration of this product over this interval is 0. Okay, 0 here. So any questions about the statements of this theorem? Okay, and the proof. Right. So we say the proof, okay, can be completed by applying sum and difference identity in trigonometry in particular, I think if you want to prove the first items, you can use the antiderivative. Okay. So so for example, 1, the antiderivative of cosine and x and sine and x, derivatives are 1 over n sine and x and minus cosine and x because when you take the derivative, you get cosine nx, right? And when you take the derivative of this function, you get sine nx. Okay, so the antiderivative of these two functions, because these two functions are integrand of these two integral, right? So they are integrand. Okay. By the way, if you because sometimes this is the English speaking class, so if you don't understand any mathematical terminologies in English, just let me know. Okay, I can translate it to you. Yeah. But gradually, because I will use the same terminology again and again, right? It will be repeated to be used in this lecture, in this class. So eventually you will be familiar with all these terminologies. Okay, so this is the antiderivatives, okay, of them. So that I think you all learned this from calculus. So that becomes to be okay. And remember, n greater than equal to 1, so n always positive, okay? And so that, so we have okay, so that this is 0 minus 0 is 0, of course, right? So it's quite easy to obtain the result, okay? And similarly, okay, so this is okay, but as we know, cosine function is an even function, so that cosine n pi is minus cosine n pi. Okay, so cosine minus n pi is equal to cosine n pi, because cosine function is an even function. Okay, even function, and so that they cancel each other. So this is 0. Okay. Okay, and the so-called sum and difference identities in trigonometry is as you can see, the sum difference is that the sum identity, say cosine theta 1 plus theta 2. Okay. Maybe I write here, know that cosine theta, maybe I will cosine Okay, first of all, we have the sum angle formula and the difference angle formula, right? So this is the four famous identities we have, right? And from here, we know if we want to have the product sine theta 1 cosine theta 2, if we want to have this one, we know we can add them together and divide by 2. So this is the 1/2 of sine theta 1 plus theta 2 plus sine theta 1, 2. Okay? So like we can, so this is called the sum identity to obtain this product. Okay. If we want to have this cosine and theta 2, then we take the difference, right? Okay. Now to find the product of two cosines, okay, and so we can have the half of the sum of two cosine functions. Okay, so you can obtain that okay, all right. So you can, so you want to evaluate, for example, the integral of the product of two cosine functions. You use this formula here. Okay, you can use the formula. So that so if we want to evaluate C cosine pi cosine and pi, okay, and then that, okay, so you can apply this formula, right, and so this is cosine n plus n pi here plus cosine n minus n pi here. Okay, so you can apply this one. So theta 1 is n pi and theta 2 is n pi. So you can have this one. And by the linearity of definite integral, so this is as we see. So this is cosine n plus n pi, okay, dx plus cosine n minus n pi dx here. Okay, and now you can use the antiderivative of cosine function and sine function. Okay, okay. So so this is 1/2, and the antiderivative of this integrand will be I'm sorry, x, sorry. So the antiderivative will be n plus n, 1, and the sine n plus n x. Okay. And the other one, x. Here. Now, because n and n are not equal, so the difference never 0. Okay, so you can have that. Okay, and as we know, when we substitute the ending point pi here or minus pi here, we have an integral number of pi, so the value always is zeros. Okay, so you can have like a minus 0 plus 0 minus 0. And so this is 0 again. Okay, so this shows that in this case, this is 0. And the other, for this case, you apply the formula here. Okay, you apply this formula, and you will get the same result. Okay. For this case, cosine nx, you can use the second identity here. Okay, and okay, so anyway, so similarly, we have that. And okay, right. So when we use in this case, then when n equal to n, when n equal to n, then we will see that the difference here is 0. So sine 0 is 0 already. Okay. So only this term will be considered only. Okay. So anyway, that you can show the result. Okay. So it's quite easy to have. So any questions? Now, we will exhibit the importance of trigonometric system. Right, so our trigonometrics series expressed like this one, A0, and basically it's A0 times 1, okay, plus A1 cosine x plus B1 sin x plus A2 cosine 2x plus B2 sine 2x plus dot dot dot, and an cosine nx plus bn sine nx plus dot dot dot. Okay, so that this is it's a series sum of functions. Okay, so this we can write it in the following way. Okay, so this is a series sum. Okay, and in calculus, I believe you learn, okay, how to determine that a series sum of functions, okay, converge or not. Okay, right. So this is a series. Okay, explore this one, where A0, A1, B1, A2, B2, dot dot dot, AN, BN, dot dot dot, are constants. Alright, so they are constants, so we can give these constants. Okay. Alright, so this is series where B a periodic function. Okay, a periodic function with a period 2 pi. If the series converges, okay, for all x in R. So if this series converges for all x in R, then of course this is a periodic function. Okay. Okay. The reason is that if we x plus 2 pi and we find that this is equal to, because cosine x plus 2 pi is equal to cosine x, cosine, oh, sorry, n here, I forgot to put n. So this is the cosine nx plus 2n pi, or, well, I think that's fine, just nx, because 2 pi is a period of all this is sinusoidal functions. So we have this identity here. Okay? Right, so any trigonometric series, if it converges for all x in R, then this series actually becomes to a periodic function with a period 2 pi. Okay? So we will have a question. So we will have a question. The question is that, can a periodic function f with a period to pi be expressed, okay, as a trigonometric series, i.e., can we express fx as such a series sum okay, for all x in R, okay, for some A0, A1, B1, A2, B2, da da da, AN, BN, da da da. Okay? So this is a mutual question. Okay? And in this section, we will try to answer this question. Okay? And to see under what conditions that this answer is yes. Okay? Okay, so let's take a break up to 2:25. Okay. So now we are going to answer this question, at least partial, give a partial answer, right? Now, so we are going to find conditions for a periodic function such that this periodic function can be expressed by this trigonometric series. Okay, but before to have a sufficient condition, an easy way is to find the necessary conditions. Okay, so suppose that we have a periodic function which can be expressed by a trigonometric series. Then what happens? What do we have? Okay, so if this is true, then what condition can we have? Okay, so assume that f of x, so a periodic function with a period 2 pi can be expressed by a trigonometric series. Right, so assume that but here we just say for almost all x in R. Okay, which means that the partial sum function, so the partial sum function x sub n of x, which is a0 plus n from 1 to n, an cosine nx plus bn sin nx. Okay, so that the sum is only finite terms. Okay, so this partial sum function converges to f of x as n goes to infinity for almost all x in R. Okay. Now, I have to explain what do I mean almost all. Okay. Right, so I give an explanation. The concept of almost all. Okay? Right. So we let script n to be such that xn of x does not converges to f x as n goes to infinity. Okay? So when we say almost all, means that some x, for some argument x, that the partial sum function, because as you can see, the partial sum function is a well-defined function. Why? Because they are a finite, a linear combination of a finite number of sinusoidal functions, okay, plus constant. So you see, these functions, the partial sum functions is well behaved. For example, x infinitely differentiable, right? You can check any derivative, any order of derivatives, okay? Here. But for some x in R, this partial sum function does not converge to f of x, okay? And we collect all such x together to form a set called N. Okay, so the N is here. Right. So if the length of N, okay, so because that so in the real line, they must have some points, okay? So that, okay? So for all these x, okay, so they are, so the n consists of these discrete points, for example. And as we know, the length of the point is 0. Okay, the length of the point is 0. And if we have countably many points, okay, here, then the total length of this point is also 0. Okay, so if the length of n is 0, then that and is called then xm is called then xm converges to f of x or almost all x in R. Okay, so this is the concept of also almost all. So of course it's not all, or possibly not all, but if we collect all x such that the partial sum function does not converge to fx, then the total length of this set n is 0. Okay, still. So it is possible that n consists of countably many points here. So for example, these are points in n, okay? And the total length of this point altogether is 0. Okay. If it's uncountable, then the length of n may be greater than 0. Maybe or may not. Yeah. Okay. But if it is countable, then of course the length of n is 0, of course. Yeah, the major, because we use length as a major. Yeah, so the major is 0. Okay. Okay, all right, so we just saying that we just assume that this trigonometric series, can represent this periodic function for almost all x in this sense, okay? By using the partial sum function here, and this partial sum function converges to f of x, okay, for almost all x in R. And we further assume that 1, if we consider a function, a magnetic function, okay, which is okay, so we consider this function. So we take the absolute value of each term. Okay, and this function converges for almost all x. Okay, and the second, the integral of g of x is finite. Okay, so it's integrable. Right, so we assume these two conditions. Okay, and the remark is that a sufficient condition for 1 and 2 to be true is that the series sum of numerical numbers is finite. Okay. The reason is that because the absolute value of any cosine function is upper bounded by 1. Okay, so that this term y is less than equal to n, and this term is less than equal to bn. Yeah. So the reason is that g of x is always less than equal to 0 plus for all so if this series sum is finite, then of course every x, for every x that this series converge. Okay, because the function value always negative. Okay, so that the partial sum becomes to higher and higher, right? Okay, so the partial sum has larger and larger value as n goes up. And because that it has an upper bound, okay, so by this the accent of communality then if it has upper bound, then it will have least upper bound, and this upper bound will be the convergent value. Okay, so that this condition, okay, guarantee that this series converges for all x, not just for all mod O. If we have this, okay, so that so this condition, and indeed this is sufficient. Okay, guarantee sufficient guarantees that f of x, okay, g of x converges for all x in R. Okay? Not just for almost all, issue for all. Okay? It's for all. And it is quite easy to justify whether this series sum is final or not, okay, in general. Then I believe you learn some techniques to do the justification. Okay, so once this is true, then g of x converges for all x in R. Okay. Yeah, but in all theory, we only require that this function, this series converge for almost all. Okay, because when it is converged for almost all, we can evaluate this integral. Okay, so the integral, for this integral, it has value for almost all x in this interval will be enough. Okay, will be enough. Okay, so we have this is requirement. Okay, right. So now the situation is that this series, okay, this series is equal to f of x, okay, for almost all x. Okay, so the representation is good for almost all x in R, and we require two additional conditions, 1 and 2. Okay, for there. Right? Now we will derive some useful necessary conditions. But before that, we need an important theorem in analysis. So before further derivation, we state an important theorem in analysis. Okay. And this theorem is called the dominated convergence theorem. Yeah. So we let f and fn and from 1 to etc. be functions be complex or real-valued function defined on an interval I. And this interval could be finite interval or infinite interval. Okay. Such that f of x converges to f of x for almost all x in R. Okay? So suppose that we have a function f and a sequence of function f sub n. Okay? Oh, functions, I'm sorry. Defined on an interval, okay, I. Such that in I, sorry. Such that the function value fn of x converge to f of x for almost all x in I. Okay? In the defining interval. Okay. Now, if fn are absolutely integrable over I, which means that if we use the value of fn as the integrand and take this integral, okay, which is finite. Okay. So which means that this integral is finite means fn is absolutely integrable. Okay. And there exists, okay, an absolutely integrable magnetic function G over I such that each f sub n is dominated by this G function. Okay, So the main denominator means that every f sub n, okay, is dominated by this negative function g of x. Okay. And for almost all x in I. Okay? So there are several conditions. Then our conclusion is that f is absolutely integrable over I, i.e. Okay, and the very important thing is that the integral of x, because okay, because f of x is the limit, right, of f of x for almost all x, right, in I. So f of x is the limit, and this limit can be evaluated by evaluate the integral of fn first, and then take the limit. So the important thing is you can exchange the limiting process with the integration. So it's exchangeable. I'm sorry? Evaluation? Integration here. But it's integral. Okay, so in here the integration can be in terms of the Riemann integral or the Bagger integral. Okay. Yeah. I'm sorry? At delta x. Well, you can, in general, that this is it can be as general as the Bagger integral. Or in terms of the classical Riemann integral, if we can do the Riemann integral here.
Also, some of them just cannot use Riemann integrals, and you need to use them.
Yeah, and the term here, you have to use the Bagger integral.
That will always work.
Yeah, always correct. But if the Bagger integral can be evaluated in a Riemann sense, then you can just evaluate the Riemann integral. Okay. So here, because I want to go to detail, I just say integrable. Okay. So to avoid the further technical terminology. Okay. Yeah. So this is true for the Bagger integral. Yeah, it's true for the Bagger integral. Yeah, but in our applications, in many practical situations, you can evaluate the Bagger integral by using the Riemann integral. Okay, so that would be okay. The important thing is to give you the condition when you can exchange the limiting process with the integration. Because in here, to evaluate the integral of this limiting function f of x, because f of x is the limiting function of the sequence of function f of n, right? So So f of x converge to f of x. Of course, here is for almost all x. So basically, f of x is equal to the limit of x for almost all x here. So the evaluation of f of x, okay, under the integral over the interval I, is basically first of all you have to find the limit and then to integrate over the I here. But you can do it another way. First of all, you can evaluate the integral of f of n over I. Okay, and then take the limit. Then take the limit. Okay, so but what you can do, okay, it depends on the condition, right? So the condition is here that you have an absolute integrable magnetic function G, first of all, okay? And this G dominates f sub n, okay? For almost all x in I. Okay. So this dominating function should be integrable over I. Okay? Should be integrable over I here. Okay. Once this is true, then we will know that f itself is also absolutely integrable. So you can evaluate the integral absolutely. Okay. So once this is true, then this integral without the absolute value also true. You can evaluate this integral. All right, and to evaluate this integral can be done by evaluating the integral of fn first, and then take the limit as n goes to infinity. All right, this is always the easier part to do. Okay, so now here, we can apply the dominating convergence theorem to our situation here. First of all, what is our Fn? The Fn are partial sum function here. Okay? And so Fn is our Sm, the partial sum function. And here we assume the partial sum function converge to f of x, right? For almost all x. Right here in I. Okay, but so the interval I, okay, we just take a period. Okay, even though this is true for all I, but because the periodic function is period to pi, so that the partial sum function converges to f of x or for almost all in one period, for example, from minus pi to pi. Okay, if this is true, then of course it's for almost all x in R, because the partial sum function and the f of x are periodic function with a period to pi. Okay, right. So xm here is fn, and we have the convergence here. Second thing, we assume we have g of x. Okay, so this is g of x converges, right, and integrable, so that the g of x is absolutely integrable over I. Okay, so we can here I is equal to this interval. Okay, so it's a finite interval. Okay, and it is clear that every xn is dominated by g of x. So you can see that xn okay, for almost all x in R. Okay, so the partial sum function is dominated by g of x. Okay, by g of x. Okay, so by our assumptions, all the conditions in dominated community theorem are valid. Okay, and so in this case, so the function of the conclusion of this theorem, f the function of x absolutely integrable. Okay, and so this is true, and the integral of f of x can be evaluated by using this formula here. Okay. All right. So this is our observations. Okay, so now we are able to derive necessary conditions. Okay, so now we have that, just like what we have done, the partial sum functions so the partial function, when you take the absolute value is less than equal to the sum of absolute value of each term. Okay, so of course, for every n, we have this upper bound, and it will extend to an even series. So of course, this is also true. And this is g of x. Okay. All right. And for almost x in I here. Okay, so we restrict ourselves to this finite interval. Okay, and by the dominated convergence theorem, we know f is absolutely integrable, okay, over this finite interval, over minus pi to pi, i.e. this is finite. Okay, so this is finite, and okay, so we have that, and when we want to evaluate the integral of f of x, okay, now this is so this function f of x is the limit of the Parkinson function here. Now we are able to exchange the integration and limiting process because of the theorem here. So now we are able to here. And what is the Parkinson? Because the Parkinson function is here. Okay. So that this is equal to A0 plus summation AN cosine NX plus BN sin NX dx here. And by linearity of integral, so this is equal to n. Sorry, n, okay? So this is limit n goes to infinity, and here is 0 dx plus summation. Oh, I'm sorry, my mistake. An cosine nx plus bn sin nx. This is n, but n from 1 to n. Okay, and an cosine nx dx plus bn sin nx dx. Okay? Yeah. Now, by the orthogonality theorem, this is 0, right? This is also 0. Okay? So we have limit n goes to infinity. Now the first integral x 2 pi a0, the full integral, okay, and plus summation n from 1 to infinity, that's an times 0 plus bn times 0 here. Okay, so this is the limit n goes to infinity, 2 pi is 0, okay? And so this term is independent of n, so that we have 2 pi is 0. Okay? So the evaluation of this integral becomes to be easy because we exchange the order of integration and then the limiting process. We exchange them. Okay, so that we can have. And so the conclusion is that in this case, the A0 is equal to 2 pi dx. Okay, so the first, we know that then we can actually find the constant coefficient A0 through this integral. Okay? Alright, so I stop here, and Thursday we will continue to find out that once we have this condition, we can find, in addition to A0, we can find the AN and the BN, okay, from F, okay, from F, from F. Any questions? Okay, if not, then I'll stop here and I'll see you on Thursday.